Welcome to AI Paper Podcast. We're your regular source for deep dives into the latest and greatest in AI research. Today, we're tackling something really fundamental, a challenge that's honestly been bugging multimodal large language models, or MLLMs, for a while now. Truly getting video. I mean, it's not just the sequence of pictures, right? It's dynamic, it's packed with information and capturing all those subtleties. Well, that's been super tricky for AI, so our focus is the Kwai Keye-VL 1.5 technical report, hot off the press, basically, published September 5th, 2025 from the key team over at Kuaishou Group. This is an 8 billion parameter model, and it's hitting state of the art, especially, as you might guess, in video understanding. And there are three big reasons why, three core innovations we need to unpack. First up, there's this really novel slow, fast video encoding strategy. It's smart. It allocates compute based on how much the visuals are actually changing. Super important for efficiency. Second, they've got this progressive 4-stage pre-training method. And this is wild. It pushes the model's context length from 8K tokens all the way up to 128K. Think about that. It's like teaching it to remember a whole movie plot. And third, a really comprehensive post-training pipeline. This is all about boosting reasoning and aligning the model with, human preferences using some advanced RL techniques, makes it smarter, more reliable. The bottom line, Keye-VL 1.5 isn't just great at video, it holds its own on general multimodal benchmarks too. It offers some really practical steps forward for next-gen AI. So yeah, if you're an AI researcher, ML engineer, need any of this paper, definitely one to know.
Okay, let's dig in then. Why has video understanding been such a persistent headache for these models? They're amazing with static images now, so what's the big hurdle with video?
Yeah, it really boils down to the nature of video itself. It's just fundamentally more dynamic, right, and way more information dense than a single image. The core struggle for most models has been this trade-off. You want fine-grained spatial detail, which means you need high resolution.
Right. See all the little things.
Exactly. But you also need broad temporal coverage. You need to process lots and lots of frames to understand what's happening over time. And current methods often kind of stumble here. They might use uniform frame sampling, like taking every 10th frame, or stick to a fixed resolution.
Which means you miss stuff.
Totally. It's like you either lose the fine details because the resolution is too low, or you lose the plot because you're not seeing enough frames to get temporal consistency. It's this constant compromise.
Okay, that makes sense. You're always sacrificing one for the other. So this slow, fast strategy from Kai, how does it actually break that compromise? You said it's ingenious.
It really is quite clever, because it's not just throwing more compute at the problem. It's about being smart with the compute you have.
No.
The slow-fast idea is basically dynamic allocation. It looks at how similar consecutive frames are.
Okay.
Think of it like this. If not much is changing visually, why spend a ton of processing power on every single frame at high detail?
Yeah, that seems wasteful.
Right. So they have two pathways. The slow pathway kicks in for what they call keyframes. These are frames where significant visual changes happen. These keyframes get processed at higher resolution, capturing that important detail, but fewer frames overall get this treatment.
Okay, so high detail for the important moments.
Exactly. And then there's the fast pathway. This handles the frames in between where things are relatively static. These get processed at lower resolution, saving compute, but with higher temporal frequency, meaning more of these frames are included to keep the sense of motion smooth.
Interesting. So how does it decide what's a keyframe versus a static one?
That's the neat part. They use a patch-based similarity function. Imagine breaking the frame into little squares or patches. The very first frame is always processed by the slow pathway, high res.
Got it. Starting point.
Then, for the next frame, it compares its patches to the patches of the most recent slow frame. If the similarity is really high, they use a threshold of 95%.
Okay.
It says, all right, not much changed, and sends it to the fast pathway. Lower res, less compute.
But if the similarity drops below 95%?
Then bam, it flags it as a new keyframe. Significant change detected. Back to the slow pathway, high-resolution processing.
So it's genuinely adaptive. It's watching the video content itself to decide how hard to work. That's cool.
Exactly. It's not just blindly sampling.
How does this play out with the token budget? Because that's always the big constraint with these models, right? Especially with long videos.
Huge constraint. And this strategy is very efficient. A fast frame, the low-res one, only uses about 30% of the token budget of a slow, high-res frame. And there's an overall budget cap, of course. For Keye-VL 1.5, it's around 75,000 tokens total for the video input.
And they track the timing.
Yep, they use special tokens that actually have absolute timestamps embedded in them. This marks the boundaries between slow and fast segments and helps the model keep track of the timeline accurately.
Okay, so let's talk results. You mentioned figure 7 in the paper compares it to, say, Kwai 2.5 VL.
Right, and the difference is pretty stark. Kwai uses a more traditional 2D convolution approach. Keye-VL 1.5 with slow-fast shows much better integration of information across many frames. For example, on benchmarks like Video ME, Kye's performance actually keeps improving and peaks much later, like around 384 frames, whereas Kwai might peak earlier, say 128 frames.
Meaning it actually understands longer sequences better.
Precisely. It's not just looking at short snippets. And the adaptive token usage is key. It uses more tokens when needed for complex scenes early on, but becomes more frugal as the frame count increases, showing real efficiency.
And it's stable across different frame rates.
Yeah, much more stable performance compared to fixed sampling methods, which can really struggle if the input video FPS varies a lot. This is much more robust for real-world video.
Okay, that slow-fast encoding sounds like a really significant piece of the puzzle for efficient seeing. But you mentioned the other challenge, remembering what you've seen over potentially long durations. How do they tackle that huge context length extension, getting it up to 128K tokens? That sounds massive.
It is massive. And they didn't just, flip a switch. It was this very deliberate, progressive, four-stage pre-training pipeline. You can see it laid out in figure 4 of the paper.
Stage by stage, right?
Yeah, exactly. Building it up carefully. So first, there's the foundational VIT Pre-training. This is about getting the vision encoder really solid, focusing on image text matching. They start with a strong base, SIGLIP 400M, but they enhance it significantly. One key thing is native dynamic resolution processing.
Meaning it doesn't have to squish or crop images.
Right. It preserves the original aspect ratio. This sounds subtle, but it means the model sees shapes and objects more accurately, without distortion, less information loss. And crucially, they integrate 2D rotary position, embedding rope.
Ah, rope E. We hear about that a lot. Why 2D here?
Well, standard rope E is often 1D, applied like text. But for images, 2D rope E gives the model a much better sense of spatial relationships, like where things are relative to each other in the 2D plane of the image. Better geometry understanding.
Makes sense. Better map of the image.
Exactly. And this stage uses a huge data set, 500 billion tokens, from sources like Datacomp, LERON, Kokite, plus their own in-house data.
Okay, so solid vision base. What's next?
Stage 1 is Cross-Modal Alignment. Here, they actually freeze the vision transformer, VIT, and the LLM, which is Kwai 3.8b in this case. The focus is purely on training the MLP projection layer that connects them, getting that visual linguistic bridge really strong and aligned.
So just tuning the connection.
Right. Then stage 2 is Multitask Pre-training. Now everything gets unfrozen. VIT, LLM, projector, all trained end-to-end. And they hit it with a really diverse set of tasks. Image captioning, OCR, visual question answering, grounding, locating objects, even interleaved image text data. This builds broad multimodal capabilities.
Okay, building up the skills and then the big context extension.
That happens in stage 3, annealing and long context extension. They fine-tune on high-quality data first, and then they make the jump. Context length goes from 8,192 tokens, the 8K, up to 131,000 to 70 to 128K. This involves resetting the rope inverse frequency scaling on the LLM side, basically recalibrating its sense of position over much longer sequences.
Like giving it much longer range vision within the text sequence.
Kind of, yeah. It allows it to handle relationships between tokens that are much, much farther apart, essential for understanding long documents, or, in this case, the descriptions and reasoning derived from long videos.
And how did they allocate tokens in that huge 128K window?
It was a strategic split. About 24% reserved for video representations, 50% for images, so still very strong on static images, and 26% for pure text, finding that balance.
Wow. Okay, so we have efficient adaptive vision with slow fast, and now this massive context window from progressive pre-training. The model can see well and remember a lot. But raw capability isn't everything, right? How did they refine it? Make it reason better, align it with what humans actually want or expect.
That's exactly where the post-training pipeline comes in, and it's arguably just as sophisticated as the pre-training. This is figure 5 in the paper. It's all about enhancing reasoning and achieving that human alignment.
How does that start?
It kicks off with what they call the non-reasoning stage. This combines 2 techniques: supervised fine-tuning, SFT, and mixed preference optimization, MPO. For SFT, they used a massive data set, over 7.5 million high-quality, multimodal question-answering samples.
7.5 million. Wow.
Yeah, and crucially, it's diverse. They use something called Task Galaxy to ensure coverage over like 70,000 different types of multimodal tasks. So it's not just simple Q&A. They also made it challenging by using other MLLMs to generate complex reasoning path, filtering out easy stuff, And they ensured reliability with human annotated captions.
And MPO, Mixed Preference Optimization.
MPO comes after SFT. It refines the model further, using pairs of responses where one is preferred over the other. This data comes from various sources, open-source datasets, text-only preference data, and human annotations, all guided by a reward model.
Okay, the reward model. This seems critical for alignment. But how do you build a reward model that isn't just incurring its own biases? How do they make it robust?
That's a great question. And they put a lot of thought into their key reward model. It's not just a simple score. It actually has two modes, think and nothing. Nothing gives a direct judgment. But the think mode is more interesting. It evaluates the model's response along 9 specific dimensions.
9? Like what?
Things like credibility, correctness, detail level, redundancy, relevance, safety, a whole range. This multidimensional evaluation helps provide more nuanced feedback than just good or bad. It guides the model towards more reliable and helpful outputs.
So it's assessing the quality of the response in multiple ways.
Exactly. Now, building on that, they focus specifically on reasoning with long cold start, COTI meaning chain of thought. They have this really cool 5-step pipeline for automatically generating high-quality reasoning data. It's shown in Figure 6.
Automated reasoning data generation. How?
Okay, so first, they collect multimodal QA data from tricky domains, math, STEM, OCR, even things like graphical user interface understanding and business charts.
Diverse sources.
Yeah. Second, they use existing MLLMs to generate multiple possible reasoning paths for each question, not just one answer. And they quantify the model's confidence at each step. Third, a 2-level quality assessment checks both the final answer's correctness and the validity of the reasoning steps used to get there. This categorizes data into high A, moderate B, or low C quality.
And humans are involved.
Yes, that's step 4, human-in-the-loop refinement. Humans review the moderate B samples and potentially redundant A samples to fix errors or improve the reasoning paths. Crucial for quality control.
Makes sense. Catching things the AI might miss.
And finally, step 5 is a dynamic 5-point quality scoring system. This allows them to prioritize the absolute best reasoning data during the cold start fine-tuning.
Okay, that's a very structured way to build reasoning data. What about specific weaknesses? Did they find any?
They did. They identified areas where the base model could be stronger, like pure text tasks, math, and especially OCR, so they used model merging with domain-specific experts.
So train smaller, specialized models and merge them in.
Pretty much. They give the example of an OCR expert. They trained a model specifically on datasets for things like license plates, street signs, official seals, tricky OCR scenarios. They even used an MLLM pipeline to generate more training questions automatically. Then they fine-tuned the specialized model SFT to create the OCR Expert. Merging this expert into the main Keye-VL 1.5 model gave a significant boost in OCR performance. Table 7 shows it going from about 78% average accuracy to over 84%.
That's a solid jump. Is there a risk, though, that merging in an expert like that could maybe dilute its general abilities elsewhere or make it less flexible?
That's always a potential trade-off with specialization. But their approach seems focused on careful modular integration. It's not replacing the core, just enhancing specific skills. Plus, the subsequent RL stages help reinforce general capabilities.
Okay, so what are those RL stages?
Next comes Iterative General RL. They use an algorithm called GSPO Group Sequence Policy Optimization. It's a form of RLVR, reinforcement learning with verifiable rewards.
Verifiable rewards, meaning you can check if the reward is justified.
In essence, yes. It encourages the model to generate responses, particularly reasoning steps, that are inherently checkable or verifiable, building more trust. And here they use a technique called progressive hint sampling for the really tough problems the model keeps getting wrong.
Giving it hints.
Yeah, but in a structured way. They have 5 levels of hints, following a minimal intervention idea. Level 1 might just be a conceptual hint, while level 5 is basically the full solution.
And does it help?
Dramatically. Table 9 shows that error rates on these hard cases dropped from over 25% with no hint down to just 0.2% with the level 5 hint. It makes difficult training samples actually useful for learning instead of just frustrating the model.
That's clever. Turning failures into learning opportunities.
And this whole RL process is iterative. The improved RL model helps generate better data through rejection sampling for the next round of SFT or cold start training, which then leads to a better RL model in the next iteration. It's a continuous improvement loop.
A virtuous cycle.
Exactly. And finally, there's Alignment RL. This focuses specifically on making the model behave well in real-world applications. It targets 3 dimensions. First, instruction following. making sure it adheres to specific constraints on content, format, length, etc. They use like 25 hard constraints and 20 soft ones.
So actually doing what you ask it to do.
Precisely. Second, format adherence, making sure it outputs responses in the desired structure, like the think-answer format or others they define. And third, preference alignment for open-ended questions, improving things like reliability, how interactive it feels, its writing style, making it generally more helpful and pleasant to use.
And this is all guided by rewards again.
Yep, a sophisticated reward system combining rule-based checks, generative models, using other MLMs to assess things like reasoning quality or ethics, and model-based rewards trained on human preferences. It's a multi-pronged approach to ensure the final model is not just capable, but also aligned and safe.
Wow, that is incredibly thorough. It sounds like they really thought through every stage, from pre-training efficiency to fine-grained alignment. So, okay, the big question. What does this all add up to in terms of performance? For us researchers and engineers out there, what's the payoff?
The payoff is pretty significant. If you look at their main results, like in Figure 1 or Table 3, Keye-VL 1.5 achieves state-of-the-art or very close to it on a lot of standard vision language benchmarks and even mathematical reasoning tasks.
Just competitive generally?
Very competitive. But where it really shines, its standout advantage, is in video-centric scenarios. That's where the slow, fast encoding and long context truly pay off. For instance, on Video MMMU, which is a tough benchmark for multimodal video understanding, they report an absolute improvement of 6.5%. That's a really noticeable leap.
Yeah, 6.5% is substantial in these complex tasks.
Absolutely. And it holds its own against even powerful proprietary models like GPT-4o and Claude 3.7, especially considering it's an 8 billion parameter model, which is relatively modest compared to some giants.
And you mentioned they built their own benchmarks too. Why do that?
Right, that's in Tables 4 and 5. They did that because, frankly, public benchmarks often have limitations. Sometimes the task coverage isn't broad enough, or the questions are too simple, or there are worries about data contamination where models might have seen the test data during training.
Or cultural bias, maybe?
Exactly. Language or cultural biases can creep in too. So by creating their own internal benchmarks, they could test for specific capabilities they cared about, maybe more complex reasoning or robustness to noisy data. And their internal results really highlighted Keye-VL 1.5's strengths in areas like reasoning ability, understanding temporal information in videos, and overall robustness, where it scored notably higher than comparable models like MLLMs.
So strong on public tests, even stronger on their tailored internal ones. Makes sense. And presumably none of this happens without some serious engineering on the infrastructure side.
Oh, absolutely. You can't train a model like this, especially with 128K context length and complex video processing, without optimized infrastructure. Section 5 touches on this. They used a heterogeneous hybrid parallel strategy. That means combining different parallelism techniques, data, pipeline, tensor smartly, because the vision transformer and the LLM have different computational needs.
Adapting the parallelism to the model part.
Exactly. They also implemented dynamic load balancing. This is clever. It estimates how long each training sample will take to process. Complex videos take longer. And distributes them across GPUs intelligently to keep everything busy and avoid bottlenecks.
Preventing GPUs from sitting idle waiting for hard samples.
Precisely. And to handle the massive I/O demands of loading video data, they built a flexible and scalable data loader. It uses separate I/O servers to offload heavy tasks like video decoding for the main training CPUs. They even have an instance-level perfect resume mechanism, which means if training gets interrupted, it can pick up exactly where it left off for each individual data sample. Super important for stability in long training runs.
That infrastructure sounds like a project in itself. Okay, this is all very impressive technically. Let's make it even more concrete. Can you share a couple of those case studies from the appendix, just to give us a real feel for what it can do?
Sure thing. They have some nice examples. Video case. It was about grounding. The task was to find exactly when a specific object, I think it was a handbag, appeared in a video.
Pinpointing it in time?
Yeah, and Keye-VL 1.5 nailed it, identifying the period from 22.3 seconds to 23.8 seconds. That's 0.1 second precision. Think about that for video search or analysis.
Wow, that's incredibly precise. What else?
Video case 2 focused on content understanding, more about social interaction. There was a video of a big dog biting a smaller dog's ear.
Okay, sounds potentially bad.
Well, a model didn't just describe the action, By linking the video to captions, it inferred the purpose. It determined the big dog was actually correcting the little dog for trying to steal food. It even mentioned this kind of educational correction behavior in dog tags.
So it got the nuance, the intent behind the action.
Yeah.
That's pretty advanced understanding.
Right. It's not just object recognition. It's interpreting behavior and context. And one more, video case 3 on content description. The scene was hail falling in a forest. The model provided a very detailed description. Dampness, moss on stones, the misty look.
Did it identify the hail?
Interestingly, it missed the specific word hail, but it did correctly identify precipitation. And the rest of the description was spot on, capturing the whole atmosphere of the scene. Shows really comprehensive visual grasp, even if specific vocabulary is sometimes missing for less common things.
Those are great examples. They really showed the difference between just processing pixels and actually understanding the dynamics, the context, the details within a video. It really feels like a significant step up.
I agree. It's the combination, I think. That clever, slow-fast encoding for efficiency and detail, the massive context from the progressive pre-training, and then all that careful work in post-training to refine reasoning and alignment. It adds up to something genuinely powerful for video.
Absolutely. Keye-VL 1.5 definitely feels like a major leap for MLMs, especially in tackling this really challenging domain of video. It moves us closer to AI that can truly perceive and comprehend the world as dynamically as it happens. So the final thought for everyone listening, especially the researchers and engineers tuning in, as models like Keye-VL 1.5 get this good at understanding video's dynamic nature, what happens next? What kinds of applications, maybe ones we previously thought were impossible, suddenly become feasible? How might this deeper understanding of video change how we interact with digital content, or even how we build real-world intelligence systems in the, very near future? Lots to think about there. A huge thanks for that deep dive into Keye-VL 1.5, and thank you all for joining us on AI Paper Podcasts.